Imagine picking up a stone and throwing it into the air. What would you say if, instead of seeing it slow down as it rises, you saw it accelerate, moving away upwards ever more rapidly? It would be a rather surprising and bizarre scene, right? And yet, something similar is happening in the universe. In fact, the universe is accelerating its expansion, a phenomenon that we have known about for more than 25 years. However, despite the enormous progress in research, the cause of this acceleration remains one of the most fascinating enigmas of modern cosmology. How did we come to discover that the universe is accelerating, and what might be the explanations for this phenomenon? Let's try to understand it together. In 1929, American astronomer Edwin Hubble made a fundamental discovery. He established that there is a law that links the speed at which two galaxies are moving away from each other to the distance that separates them. In other words, galaxies move away from each other at a speed that increases with distance. The explanation for this law lies in the expansion of the universe, a cosmic process that causes all galaxies to move away from a common origin point, with motion that continues and accelerates over time. Hubble's law is fundamental because it allows us to determine the rate of expansion of the universe, a parameter that has become essential for understanding the dynamics of the entire cosmos. Hubble's law is expressed through a parameter called the Hubble constant, which measures the rate of expansion of the universe at a given moment. But contrary to what the term constant suggests, the Hubble constant is not a fixed quantity over time. It varies depending on the cosmological epoch in which it is measured. For example, if we measured the expansion rate of the universe in the past or in future times, we would find different values from what we measure today. This implies that the rate of expansion of the universe has changed over time, and to understand its evolution, it is necessary to understand how this rate has changed throughout cosmic history. Measuring the Hubble constant, and consequently the expansion rate of the universe, is a bit like measuring the speed of a train passing by. If we only measure the speed at a given moment, without knowing how it changed over time, we cannot be sure how far the train is or when it started. Similarly, if we want to know how the universe's expansion has evolved, we must be able to measure its speed in past epochs, not just in the present. Initially, astronomers thought the expansion of the universe behaved like the motion of a stone thrown into the air. The idea was that gravity would slow down the expansion, just as Earth's gravitational force slows down an object rising in the air. If the expansion had been slow enough, gravity might have eventually stopped it, causing the universe to collapse. If instead the expansion continued forever, it would have gradually slowed down due to gravity, which acts as an attractive force between galaxies. However, measuring the variation in the rate of expansion of the universe is by no means a simple task. To do so, one must observe galaxies at extremely large distances, which poses significant technical difficulties. To measure the distance between Earth and a galaxy, astrophysicists use what is called the standard candles method. A standard candle is a cosmic object whose intrinsic luminosity is known. Just like knowing how powerful a light bulb is, we can determine its distance by observing how bright it appears from afar. An example of a standard candle is Cepheid stars, which have a particular pattern in their luminosity variations and were used by Hubble in his early observations. However, the farther we look into the universe, the more complicated the standard candle method becomes to apply, due to difficulties in measuring luminosity and precise distances. In the 1990s, however, astronomers made a discovery that revolutionized the field of cosmic observations. They identified a new class of particularly reliable standard candles, type Ia supernovae. Supernovae are catastrophic explosions marking the death of certain stars, and type Ia supernovae are especially interesting because they are extremely bright and share very similar characteristics. These explosions, which release more energy than the entire galaxy in which they occur, are so powerful that their light can be seen even at extraordinary distances, up to billions of light-years. Type Ia supernovae form in binary star systems, where one of the stars is a white dwarf, an extremely dense object that accumulates material from its companion star. When the white dwarf reaches a critical mass, the balance that keeps it stable is disrupted, and the star explodes into a supernova. This type of explosion has the peculiarity of following a well-defined behavior. The rate at which the supernova's brightness decreases over time is closely related to its peak brightness. This allows us to calculate its intrinsic luminosity and, by comparing it with the observed luminosity, determine the distance to the supernova from Earth. The advantage of Type Ia supernovae is that they are so bright that they can be observed at enormous distances, allowing us to study the universe from very distant times. However, since they are rare events, astronomers must observe numerous galaxies over a long period to detect a Type Ia supernova. Once identified, the distance to the host galaxy can be determined, and the rate at which the galaxy is receding can be measured. With this information, an estimate of the universe's expansion rate at the time the light from the supernova left can be obtained. In 1998, two international groups of astronomers studying Type Ia supernovae made a surprising discovery. By analyzing supernovae that exploded when the universe was only a few billion years old, they realized that these supernovae appeared dimmer than expected. At least, they seemed so if the universe's expansion had been slowing down, as expected based on traditional gravitational theory. After ruling out possible observational errors and alternative theoretical explanations, the only plausible explanation was that the expansion of the universe was accelerating. The light from the most distant supernovae appeared weaker because the accelerating expansion had pushed them farther away than expected. This discovery was a huge surprise, but the data were so solid that they could not be ignored. In 2011, the leaders of the two groups that made the discovery received the Nobel Prize in Physics for demonstrating the acceleration of the universe's expansion. This radically changed our understanding of the cosmos. Until that moment, it was thought that gravity, being an attractive force, would always slow down the universe's expansion. Yet, what awaited us was a completely different reality, in which expansion accelerated, not slowed down. But why does the expansion of the universe accelerate rather than slow down? The cause of this phenomenon is one of the most mysterious aspects of cosmology. Scientists believe that the main cause of the acceleration is a form of energy called dark energy, which would be associated with empty space. According to Einstein's general theory of relativity, dark energy would have gravitational properties opposite to those of ordinary matter and energy. Instead of attracting galaxies, as matter does, dark energy would have the opposite effect, pushing galaxies to move away from each other ever faster. The simplest form of dark energy is the cosmological constant, which Einstein introduced in his early works on relativity but later abandoned. Today, many theoretical physicists are exploring different forms of dark energy and modifying the theory of gravity to try to explain the acceleration. To try to solve this mystery, many observational missions are underway. One of the most promising is DESI, an international collaboration that is constructing a three-dimensional map of galaxy distribution, examining the cosmos back to over 10 billion years ago. Another key project is ESA's Euclid satellite, launched in 2023, which aims to make even more precise measurements of the universe's structure and the effect of dark energy. We hope these observations will help solve one of the greatest mysteries of astrophysics, the cause of the acceleration of the universe's expansion and its implications for our cosmic fate. Thank you for watching. Leave a like, subscribe to the channel, and hit the bell so you don't miss future videos.